Okay. Let me first come back to the homework that I sent to you, because I'm a bit worried that it was more work for you than you thought you would like. And I want to explain to you that I think it is actually quite the sort of homework that you should be excited about, because this is what you then are supposed to pick up from a course like this. I asked you something about how correct the statement is that I can take my data tonight and then next week and in another month and combine them with the data of last year and make a nice picture out of it. And the reason for that being that obviously sorry?
Could we maybe solve the quiz?
You guys?
Yeah.
Yes, of course.
Well, yeah, like
please.
just like to know, like, can you share the answers of the
yes,
quiz?
That's what I was going to do.
Oh, okay. I'm sorry.
I was explaining. I was first justifying that I put you into a lot of work, and I wanted to demonstrate to you by helping you solve it this time that in fact this is the sort of thing that I hope you will pick up from a course like this, that you can solve this sort of questions. Because we have been discussing yesterday rather extensively what the requirements are for phases to be sufficiently helpful. In fact, we are not allowed to make errors of whatever sort that are exceeding a small, and I really mean very small, fraction of a wavelength. Because you get error vectors caused by these errors that will mess up your map, your picture. So the question is it really true if I wait weeks, months, years even perhaps, before I combine all the data that I would like to combine? And do I not have a problem there? Because the baseline for a nice east-west machine, which therefore lies nicely in the equatorial plane of the Earth and therefore on the equatorial plane on the sky, that baseline sits on an equatorial plane that is not quite stationary. So there is something wrong about my statement that the sky is different, or the same tomorrow as it is tonight. That is not very completely true. And all observers know that very well, because if they don't adjust the telescope for the precession, they cannot point at a given right ascension and declination. They mispoint the telescope, because that was right for last month. So you must do something about it, because the precession is not insignificant. The vernal equinox goes around the sky at a rate of almost 50 arcseconds per annum. So it is a sufficiently large angular rate over which this plane is busy rotating, that you might have to worry about it. Now the question was, please worry about it and find out how tolerant we are for that sort of an error. Can we just forget about it? Is the question number one. If not, what should we do about it? And can we then get it sufficiently good? And is there then still a limit remaining? Well, let's first start with the first part of that question. We decided that this plane is not stationary but is moving. If we want to see whether that is bad or not, we want to do something like make sure that we do not move the telescope inadvertently by more than something like a degree of phase. By the time it is a degree, we start worrying and we start thinking about what do we do about it. I suggested you take a baseline of 10,000 lambda. So that means that I would have to worry by the time I do 1 millionth of a radian in the location of that plane, because this baseline is going in that plane, and it's going at some elevation above that plane of yesterday. And so there is a direction in the sky. If I were looking at that direction, I would see that. I'm not saying it will always hurt. It will hurt in some specific direction, and that was the question. Is it always true, or is it not always true? And if not, what do we do about it? Now, the rotation rate of the Earth, or of the Earth axis around the ecliptic pole, it goes around a cone around the ecliptic pole, takes 25,800 years. And so you can calculate how much it does in 1 year. You can even calculate that very precisely, taking proper account of the fact that that thing only goes around a small circle, not on a big circle. So the angular rate gets suppressed by the sine of the 23.5 degrees that our Earth axis is off from the ecliptic pole. That 23.5 degrees is the size of the small circle, and so the angular rate of the plane as a whole gets suppressed by that sine over that angle. So the angular rate that we arrive at times 10,000 lambda is we do in 1 year. If you do the full calculation, then you end up at the fact that the thing does about 1/10 of a radian almost in a year, 1/10 of a lambda 1 year at 21 centimeters. So that is some almost 200 millimeters. That's excessively much. That's almost already a problem after a day. And so the statement is, it is wrong to not do something about it. That's statement number one. Statement number two is, can we then do something about it? Well, yes, we can. And it's not particularly difficult, because we know exactly where this one end of the baseline, if I keep this one at the center of the plane, where this one goes above or below the plane of last year. And also by how much. Therefore, I know the phase correction to make for that given source that sits in that direction, and I can therefore make the correction if that's the source that I'm looking at. The only thing that now remains, because now I can do it perfectly adequately and perfectly right, if I'm doing it for that one source, and then I'm looking at the vicinity of that source at the same time. If I make an error in this correction, which is good for the center of the field, so that the correction is good for the center of the field, however, it is still 10 degrees off at the edge of the field, I must also make that correction. The question is, how bad does that get? And then you should realize that the field that we're looking at is defined by the primary beam of such a telescope, and of the order of, say, half a degree or something like that. Is of the order of 100th of a radian. That means that the correction over the field is at most about 1% of the correction on axis in that field. Therefore, after a year, sort of, we get into the level that we have troubles making these things completely corrected without also thinking about the correction that you must make across the field. Fortunately, we see straight away that we're talking about something that varies by as much as 1 degree from one side to the other side of the field, which is bad, but it is rather a trivial correction, of course, because in my UV plane, I must, for these observations of such a date, I must apply such a slope of phase across that UV plane. That's all there is to it. So the correction is relatively straightforward. Now, without having done any math, we have now been able to budget, estimate, and see how we can correct if we get worried about it. And it's exactly that point that I wanted you to see and recognize as something that you should have picked up from this course. That's why I gave you the tool to specify it as such. Now, I realize that not specifying it much more extensively for you makes it an awful job to do that for the first time. And yet, I hope you are convinced now that it fits exactly with what we were trying to do and understand. You want to get feel for the precision that we require of the description of the geometry in which we describe our phases, otherwise we cannot do the mapping. And this was a very nice exercise to see whether we really thought of everything. So that was the idea. I hope you're now convinced that this was not such a bad idea to make you work on that one. Okay, let's then go back to our come on. I don't know why he doesn't want to do what I'm asking him to do. Sorry? Yes, I know. That's the way I know them. I don't know. Do you understand why this guy doesn't do what I'm asking?
If you do this, about this,
There you are.
so you are trying to change the, if you put the,
No, that's the one. If he knows, we're still not there. Yeah.
zoom,
That's what I asked him to do a few times, but he doesn't do.
let's see. Let's see what happens if we disconnect this.
No, that should not be it, or possibly, but I don't understand why. Right.
This guy. Okay,
Now he's talking. Now we're talking, but he doesn't.
so let's go to the other slide. Okay, let's see.
I kill that one, and then I still say, please get going, which I do like that. There we are. No, now I still do.
Not that because, yes.
There we go.
Okay.
Por favor.
Favor, espera. Okay.
Sorry, there we are. And I don't know why he now shifts. I still don't get this thing right where I want it. Let me try once more. Okay, I'll kill it and resume all the way from below. There we go. I There we are. Again, it's a duplicate now instead of getting the slideshow.
You want to have this here.
Yeah, I'll kill it one more time and then it should work well. I don't know what the hell's going on, but I shall just start it all the way from scratch again.
I think
There
you
it comes.
will have to duplicate the. It's duplicated right now.
I shall make it projector only. Then I should be able to. Right, and now I only need to still get this thing. What the hell?
Entonces, mientras el profesor va arreglando ahí el problema, ya les voy a dar, hoy les doy los resultados de los primeros dos tests, ¿cierto? Que ya están en la página del curso. Todavía no he podido calificar el último test del curso pasado, ¿listo? Pero denme un momento, que ayer estaba en Bogotá. En términos generales, le está yendo mejor en este curso que en el anterior, ¿cierto? Entonces, obviamente no quiere decir que todos están sacando los mejores scores, pero les está yendo mejor. Entonces lo felicito porque realmente es un curso muy técnico, ¿cierto? Extremely técnico. Y aún así, pues, digamos, los resultados son buenos. Will restart your computer or something?
It looks like that, but I'm not going to do that.
Okay. Las soluciones a todo, a los ejercicios, a los exámenes de los dos cursos van a montarse también en la página del evento tan pronto terminemos. Mañana no hay clase a la 1. ¿Okay? Mañana nos vamos a reunir a las 4 para terminar. Nos reunimos a las 4 para terminar. Y no vamos a estar a clase a la 1 porque vamos a estar con los profesores en el parque, Arby. Mañana obviamente concluimos. No olviden la charla a las 6:30 en el planetario. Saquen el ratico, vayan. Los que no fueron a la charla del profesor Kuhn la semana pasada, les aseguro que es una experiencia diferente estar en la charla divulgativa y ver la cosa, digamos, ya con unos ojos diferentes. Además, el tópico es diferente y es un tópico de mucha actualidad para todos ustedes si van a trabajar en algún momento en el futuro con datos de misiones importantes. Mañana se va a hablar de Gaia, que es esta nueva misión astrométrica que va a medir la posición con precisión de 1.000 millones de estrellas en la galaxia. Muchos de ustedes posiblemente van a trabajar con datos de Gaia en algún momento en sus vidas. Entonces es interesante que estén mañana en la charla, ¿correcto? So, Mr. Rudolph, we should this is right or not?
Finally, yes. That's all right.
Okay.
Right. I'm very sorry. I don't know what got into his mind. But so, Yesterday we started looking at he's still busy doing other things. Right. See whether he does it now. Yeah. Right. We were going to look at how you make these images and the sort of defects that you can have in images. And we saw that there's a lot to discuss there. And it's good to realize how many of these details are all relevant before you can make any pictures. Mind you, you must have noticed already that I try to avoid digging into something nice and deeply so that you can do all the math properly. If I do that, then we can certainly not cover interferometry to the extent that you can get a feel for it. So I'll try and do things here and there so that you get a feel for how it works, that you also know where the difficulties will be by the time you would try and want to do it yourself, and at the same time, obviously, you will not be capable at the end of this one course to become a full-fledged interferometrist in one more week or something like that. That is not what we were achieving. What we are trying to achieve is that you understand what interferometrists are doing, which sort of quarrels they are fighting with nature in order to make their machine work properly, and what sort of property or what sort of properly working one can achieve if you do all the fine print details properly. And that is not at all easy, as you will see, and it is much too complex to get a feel for the whole full details. But you get, hopefully, from the sort of details we look at, you get a feel for the things that make the difference. And that's what you want to know, I would hope. So here is the question, have I got a decent image? And obviously this one is much less nice than that one, so the sort of answer for the time being is this one is no and that one is yes. But in fact, of course, the real issue is that this thing is pretty close to that anyway. So whether this is a good image or not for the scientific purpose that I have in mind is not necessarily implying that this is bad and that is good. I could, most of the questions that I can ask from that one, I can ask from this one as well, answer them also properly. With slight errors, the errors will certainly be bigger quantitatively than I would make here, but I should make the scientific case to really want to have the best possible details there, because obviously even that one is not going to answer my scientific questions precisely to the point that I don't need any more data or nothing else anymore. So it depends on the specification of your scientific case, whether you like an image or you do not like that. But let's first try and make just nice images. Let's see what it takes. One of the tricks to find out whether you're doing well is you look at the RMS, the noise, the fluctuations, not on the source but off the source. I've demonstrated yesterday already that any phase error you make generates a fault vector which is a quadrature. So if the proper vector is even, you get an odd fault vector out. And that fault vector is linear with the signal that you have from the source itself. The bigger the source, the bigger the vector A to the I phi that you are getting out of your measurement, and putting it differently makes a fault error which gets bigger the bigger the signal is. So that will certainly provide patterns in the background, because the power of that source then gets spread all over the place where you don't want it. And therefore, studying the off-source RMS in comparison to what you think you should have expected there is a great help to notice that something is wrong, and if you're a bit lucky you can sort of see what is wrong already. One of the other questions you might think is, does it error increase only in the vicinity of the source? Can you imagine what would be the difference if it is all over the place, or if it happens mainly in the vicinity of the source? I'll tell you, there's only low spatial frequencies in there that cause the real trouble. So apparently you have spillover in your receiving system so that you get power that is not perfectly allocated there. So you get correlations that are only, you have a covariance function in the UV plane which is relatively narrow rather than that the thing is independently making errors all over the place. And that is so, for instance, because if the source is resolved, the amplitude of the vectors that I'm trying to put on the spot is smaller at the edge of the UV plane than it is at the center of the UV plane near the one of that source. And so the intensity being smaller, I make smaller error vectors. So the high spatial frequencies are smaller, and the low spatial frequencies are high. Is the noise non-random? Do you see ripples or something like that? Very nice way of doing is, as most of these interferometers are at the same time polarization sensitive, because the radiation is collected in dipoles usually, which have only one directional sensitivity, but you can even have two dipoles into orthogonal directions, but you can also have circular and circular in the other way as a phase relation between the dipoles. So you have, in principle, you have different measurements, not only in the intensity, but separately in the linearly polarized up and down and left, right, and even in circular. And you can look at each of these pictures and see whether they deliver what you expect. If you find out that you have 120% polarization instead of a 1% polarization, you know for sure that something went completely wrong. And then you can start looking that way. Another thing that helps is you can look for the weird structures that should be there. Rings, streaks, features in the intensity that exceed the noise by a significant amount. And you can check whether the errors are additive or multiplicative, whether it's symmetric or whether they're anti-symmetric, and whether they're large or small. That's the sort of questions that answering them always helps you to try and find where to look for the source of the trouble. This one we had already covered earlier. If you have a UV plane which is very nicely sampled, let's take an extreme example in a 25-meter mirror like those of the VLA or like those of Westerbork. If I make the baseline increment significantly smaller than 25 meters, like 12 meters or 16 meters, then I have a UV plane which is nicely sampled. Basically properly Nyquist sampled. However, the inner 2 or 3 rings I cannot bring these sufficiently close together. So there's a hole in the UV plane where I have zeros, whereas nature knows that that is bullshit. There is no zeros in there. If the rest has significant numbers, then at the origin of the UV plane there should not be zero. Because there is the total power of all the sources that we're looking at. Leaving a zero in there gives trouble. And that makes for a negative ball around the source. Because the total integral over the source is zero. Because that's what I have put in, by putting in a zero at the origin of the UV plane. You can see large-scale ripples parallel to the source axis. If the source is rather elongated, you get very easily ripples in that sense. You can get large-scale structures on the source, or you can get troubles in the spottiness of the diffuse emission. Those are errors that you have made yourself usually. That's a way of treating the data where you mistreated them. And we'll come to that too. Another one, again, your own fault. Is the image big enough? Otherwise you get aliasing problems. There's another problem. We are observing what we call frequency limited function, because we look at a function which is at most as large as out there the primary beam. But the reality is that is not good. The primary beam is not zero out there. There are sources that are 1,000 times as bright as the brightest source in the field that I'm looking at. But that source is sitting there. That source could give trouble if my telescope is not sufficiently selective in direction, and that source could leak in there. And we can discuss the ways in which that can happen. You will find there's lots of very weird ways in which that can enter, and that's something you also should worry about. For a very wide picture, a large picture, you might have troubles making your averaging times incorrect. We could have done something wrong with this W term. We have explained that yesterday, that if you go in a non-east-west array, then you have baselines that change position, and they are not all anymore in one single plane. So you get troubles as a function of position in the field in your software. We have an ionosphere which changes the propagation length of the radiation coming in. And so radiation coming in here might be delayed with respect to here, just because the ionosphere is misbehaving in that sense. That depends on the wavelength we are using. If you use a very long wavelength, it goes with the wavelength squared, then you can have errors which can exceed wavelength even. So for meter wave wavelength, you get very significant troubles from the ionosphere of the Earth. Well, let's keep going forward. You can also have problems in the UV plane. It's good to realize that the errors also obey these Fourier relationships that we have been establishing. We have forced them to do that because we are calculating these errors that way. Therefore, that is a linear operation, so you can always think about what you're looking at as the proper thing plus the wrong thing. Now the problem of course is you can't find the wrong thing, but that is because here it is summed. You might possibly find the wrong thing back if you look in the other domain, in the UV plane, because there it's multiplicative. You have multiplied by the wrong thing, a complex function that has wrong phases and wrong amplitudes. And that you might possibly be able to find. You might, for instance, find that the correlator that correlates telescope number 3 and telescope number A, that correlator is sick and gives only half the signal, or gives only a squeaky signal, or something like that. And you would find it very easily in the UV plane, whereas you would have a hard time finding that in the map. You can check errors in the UV plane amplitudes. You can check for UV phase errors. And you can see that the amplitudes make symmetric errors with respect to the sources. So if I do something rather weird in the amplitudes, but not with the phases, I will see that in the map as even errors with respect to the source. And I will see odd errors, antisymmetric errors, if the error is in the phase domain. So if I make wrong phases but the amplitudes are, I will see that there. And here's where do you look if you are looking for the troublemakers. And that is usually at best in the UV plane, particularly because that is the original data. So if you have done something wrong, it is rather likely that that happened because something went really wrong. That's a few big numbers being real wrong, whereas the rest is fine. Now, a few big numbers, whereas the rest is fine, can easily be found, usually. And not anymore after a Fourier transform them, because then you have put the power all over the map. Let's look at amplitude errors. Here we have no errors, and we have a beautiful picture with a source which has 3¼ Jansky flux. That's a pretty bright source. Jansky is a standard unit of brightness for radio astronomers. It's not particularly bright. If you see the number, it is 10 to the minus 26 watts per square meter per square root of 1 hertz. So that is not very much. I once worked it out. Suppose we would have had the telescope of DeConvolution, which was one of the first ones to look at radio waves of the neutral hydrogen. In 1953 it was built. Suppose we would have had that at the time the Earth was born, and we would have had this thing look at the brightest source in the sky, which is about 1000 Jansky, and you would have collected all the flux with that telescope very carefully and put a diode on there to make it proper DC current so that you could charge a battery with it. And we would have charged the battery for the whole time up till today, from the beginning of the life of the Earth. And we would now think, I would like to see how much is in there. And you take the smallest lamp you can find and you test. Then the lamp will just barely light and it's gone. That's as much power we are as we're getting. And that source is already 1000 times as bright as this one. But for radio sources, these are already bright. But it's good to know that that we're playing that sort of game. So it is always very sensitive stuff that you're playing. Here was a problem with the gain setting of all the amplifiers for one snapshot. That is with the VLA, where you've seen these nice antenna nice UV plane things, and you see that this is recognizably the transform of that instantaneous filling of the UV plane. And they make an error of one of the snapshots. There's a few snapshots in the picture. One of them had a gain error of a factor of 10%. And therefore, that one stands out like a sore thumb on top of all the other images. If you throw that one away, the image would be better. And it would be a lot better. There's another example. And this is the example that we were saying. You can distinguish between phase errors or amplitude errors. Here you see that the error is centered on the source. And here you can see that the first zero of the error is centered on the source. So this one is an odd error, and that one is an even error. That's the way you can distinguish whether this is a phase error or whether it's an amplitude error. That helps enormously in finding back the error source and finding the source in your UV plane. Here, one antenna has a persistent error in phase, and so you see this again. This is an error that is odd in its response. It is too much on one side and too little on the other of the source. Whereas this one is symmetric, so that's an amplitude error. Here we have a very weird one. And you will only be able to get rid of that if you can find that the correlator does not give zero signal for zero output for zero signal. It's of course relatively common. If you make an analog correlator that is disturbingly common, you could very easily make an error which makes this thing read epsilon in the sine and to epsilon in the sine channel, in the cos channel, and you have a small vector that is there persistently. That's the mean of the setting. So this thing supposedly is supposed to measure zero with plus or minus the vectors that are coming from the sky, but in fact the 0 point of that measurement is not zero, but is at a small offset, and that stays put no matter what these other vectors do. And so that is as if there is a source at the center of the fringe stopping center, at the center of the field, a source which provides me with an amplitude of this much and a phase of that much, persistently. That's a very illegal source because the source is now providing me with complex flux. It has persistent phase offset, so you can see straight away that that is wrong. And this picture would be traceable as an error of that sort if I can look at how the mean of the correlator output stays put at a fixed number rather than 0. And if you do that, you find that out properly, then it goes totally away. This is much less trivial errors. You see in here there are slight ripples, a bit like that. There's ripples in this direction with a much longer period. There's ripples in that direction with yet another period. Yeah, that's better perhaps if you can turn light down here. Could you try to turn the light on it for this picture in particular? Okay, there. You can see there's ripples of this sort, that sort, that sort, and they are all at different frequencies and different position angles. Each of those ripples almost surely is generated by 1 or 2 data points which are an error. And they have so little power as compared to the total power of all the other points. However, they come in with this one bang here that says, please add this ripple on top of it. And that sticks out like this sort of sore thumb. And if you can trace those, you just throw them away. That's bad, of course. We've agreed that you shouldn't throw UV points away because putting 0 in there is bad too. But this is much bigger than an error than the going from the proper number to 0. This is like 100-fold or so much, but that still is hardly anything as compared to the total flux of the thing. But you can still recognize these points. So if you throw them out, you get a very nice picture. Another thing comes about because of our own fault. I've already said you can deconvolve the pictures because you know so precisely what the convolving function was with which you were looking at the sources. The so-called antenna pattern, as we call it, is the one that you have made yourself. It's the Fourier transform of all your UV points, where all the UV points are replaced by only unity, a unit amplitude and nothing else. If I make all these points, and that is a set of delta functions at the location where I sampled the UV plane, so the Fourier transform of the sky intensity, and that is the convolving function with which I looked at the sky. So I can calculate with the same type of Fourier transform in exactly the same way. Instead of calculating the map, I can calculate the so-called antenna pattern. That is the response pattern that we have made ourselves. And with that response pattern, you can do the following trick. You can look in the map for the highest intensity and say, I center my antenna pattern on that highest intensity, and I take 10% off from that highest intensity. So I my antenna pattern times minus 10% of the highest point that I found, and I subtract that. Then the source will, and I have now found in the meantime that right now apparently it was clear that at that location there was that much flux. And I can do that again and again and again and again. And you make errors in doing that process if you haven't got very finely located sampling points. So you must make a map which is calculated not at a regular Nyquist rate, but much narrower, because otherwise you subtract a point source at the wrong location. You cannot possibly, in the long run, get rid of a point source if you don't withdraw it at exactly the location where it's sitting. So, in order to avoid that type of errors, you must make a map which has been rather seriously oversampled, and then you can, with the antenna pattern that you have calculated, you can subtract flux that way, and you can keep going until nothing else remains than apparently noise. Now I have a set of components that makes this flux, and I can put those back and I get a very clean map. Having done that without proper size of the field in which I'm doing that, having done that without the proper sampling of the UV plane, okay, then I can make errors in there and they can cause this sort of trouble. So it is a matter of choosing the proper window for this cleaning operation that will allow me to finally get this cleaned map back. Mind you, in this process is exactly the interpolation that brings you also the interpolation into the center of the UV plane, because now I'm finding flux. I'm finding true flux. I find that I'm getting this point source out more and more and more and more and more. And I can allocate, now later on, positive flux at this location, which is stating that at the 0 point of the UV plane, I should have had at least that much. And so you can get your low spatial frequencies back by means of this interpolation scheme. And in fact, you can go even further than that. You can also extend the UV plane beyond the measured. If you have enough signal in there, you can also precisely locate where the flux came. That's why I said you must have the sampling of the map very precisely done, because you cannot withdraw a point source at locations where it is not standing. You can approximate it, but you make errors in that approximation. So the better you can find exactly the location of the point source, the more precisely can you get rid of that point source in the cleaning process. And so you can actually find yourself super resolving the picture. You can get better resolution as if you were extrapolating in the UV plane and measuring points further out. And that's exactly what you're doing. You're interpolating or extrapolating there, and you're specifying that if these points here to here are right, then I cannot have zeros out here. I should have something out there as well. And you're specifying that to some extent as well. So making so-called super resolution, you can play that game if you have enough signal in your original measurements. You can also see straight away that even with a very weird antenna pattern, let's go back to this one here. The picture that is so disturbing here is the antenna pattern of a single snapshot. So this is done in 10 seconds or 20 seconds or something like that, looking at the sky with that array, the VLA, and then looking again at some other place and then waiting for the array to change significantly and then take a new picture again. And by misweighting this one observation, you have basically the proper picture plus the one that comes out of a single snapshot. You see that's an awful antenna pattern. However, I can very well clean a picture with this antenna pattern, with this clean procedure. That algorithm, that's rather an involved algorithm, that's been played with for some 50 years almost. It was about 50 years ago that it was invented and played and worked rather well almost instantly. But since then it has been used enormously often. It allows us to get rid of very bad antenna patterns. In other words, we can actually get a very nice map by interpreting the origin of the flux much more precisely than just with an antenna pattern of that. And then once you have done that, you can restore the map, put all these points back to these components that you have found and extracted. You can put them back with an antenna pattern that you like much better, like for instance the Gaussian or so. As if you had been smearing the map with only a Gaussian. And then you get back a map without these weird antenna patterns, with proper 0 point contributions, and so the picture will get extremely much better. And I hope we'll see some of those examples. This is what you get when you do your cleaning both insufficient, and at the same time you see something occurring because I'm subtracting the flux at the wrong location, and that causes an odd, an asymmetrical, an odd error to remain, because I'm forced by my search routine to look for the highest pixel to subtract the flux time and again and again and again at the wrong location, which I cannot repair later on anymore because there is no negative source at the other locations to bring that back up. So you cannot get that repaired. What I'm doing now is something that is sort of illegal. Okay, yeah. Sorry. Here we have been cleaning, and cleaning with too much spottiness. So we have been cleaning with too wide a mesh for the locations where you subtract the flux, and with a too small an area where you do the actual cleaning, because cleaning is deconvolution, so it's a very expensive operation because every point you subtract is over the whole map. And then you do a new one, again over the whole map. So it's a very involved procedure. And here you took it easy. Here's another example, and that's much better. You do just one scale cleaning, and here it is done rather well, but you don't do it sufficiently well, because if I do it much better, or carefully, I make the subtraction and I amplify that, then you leave this sort of a pattern which is caused completely by this routine that does the cleaning. Common and hard to fight problem with very extended structures, because again my antenna pattern is a point source antenna pattern which is very narrow, and I'm trying to subtract flux on these tiny little very high resolution points, but therefore between those operations very easily can cause this structure that you cannot repair anymore then. So you must actually do the cleaning for the low surface brightness and extended surface brightness with a much more extended antenna pattern. So you make first a map with this weighting function. You remember we were talking about this problem of the weighting in the UV plane. UV plane, which you measure, and the weight here is much lower per unit area than it is here. So the weight as a function of radius, weight goes like 1 over r. And we have said already, you get rid of that problem by multiplying by r. But of course that makes your outer part of the UV plane much noisier. That's for the time being alright, and if we're talking about bright sources, that it gets noisier is not the problem. The problem is that I don't treat the data properly. So you weight it first to something flat, but then I'm still free to choose whatever I like in terms of the antenna pattern. I can choose to multiply by a Gaussian, or I might multiply by a much smaller Gaussian. And if I do that, I get a very well defined, very smooth antenna pattern. And that antenna pattern is much better defined also sort of between the pixels, because I'm so badly oversampling it in the Fourier transform to begin with. So I have a much better definition of the relation between this pixel and the neighboring pixels and the even further out pixels, and therefore I can suppress much of this trouble. And that's why you do different scales of clean. You do these scales of clean with the same data, but you make this sort of maps with different Gaussians in the picture. Missing the short spacing on that same picture. You see here we have the problem that we have not all the UV data, but we have data between 10 and 225 kilolambda. So it is between 20 arc minutes, 20 arc seconds and 1 arc second. But we do not have the 20 arc seconds to 0. And therefore we get these depressions next to the source. And you can see straight away that even the central 2 kilolambda makes already a colossal difference. It is very important to properly fill that whole gap. Thing there is what you can get with a relatively short baselines. in fact, this is done with a single dish with the Parkes telescope. The Parkes telescope is 60 meters diameter. And the rest is done with the Australian compact array. And that has a much larger baseline set, but they don't have the inner part. So that's why you see all these dark spots in here. And that gets then properly repaired by means of co-adding the data from the Parkes dish, from a single dish. And then you can properly deconvolve, and then the picture gets real neat. There you see exactly what happens if you do it completely wrong in your Fourier transform in choosing how many points per antenna pattern you are specifying in the new map. These maps, all these points you must calculate. So it's just expense. You're talking about expense, both of your time and of the computer, to calculate all these additional points. But they're all defined. The Fourier transform is defined as a smooth continuous function, which I can sample any frequency that I like. If you just do it on the shoestring and try and do no more than just Nyquist sampling, then if you must try and then subtract those that flux by means of a clean procedure with the proper antenna pattern, then you make this sort of errors and you can't repair these stripes anymore. And if you do it with the point source sitting right at the proper pixel, then you can't make those errors anymore, and then it works out well. So you have the wrong model here. You're trying to allocate flux at this location, and that doesn't quite fit, and therefore there's something remaining, but that's an odd component out here, and I see that there's too high a flux, and I start subtracting it here, and then I'm making error on error on error, and that's exactly what causes this weird pattern here. Another way of figuring out if things are right is you could worry about the quality of your model. You check whether the model fits. And you see here the data are the blue points and the red is the model. And you can see it does not fit all that well. And that helps you look for where else the errors are. That can be much more complex than this former example. Here we are looking for this source, which is sufficiently bright to give very nice amplitudes and phases. And you can see here that it fits rather well. It's the red is the model and the blue are the data. So in the UV plane, the areas that you see are outliers, errors in gain and phase, and you look at residuals tussen a model, you think you understand what you saw, and the actual data that you have taken. In the image plane, you can see whether you sort of understand the image errors as caused by the dirty beam, or whether additive or multiplicative, whether you have symmetric properties, whether you see deconvolution problems, and it always helps you then, if you can't get it properly worked out, make models and try and see whether you can cause the same trouble again in other sorts of data by the same mechanism that you might have imposed. For ALMA we have special support teams for the users of data that help you with doing this modeling and so on. But now there's still a second step. Yeah, almost. Yeah. Okay, sorry. Then we will continue hereafter with what you can do with the data in terms of analysis of the data. Of course, it's only looking at the data for what is wrong. But we don't take these data for what is wrong, we take the data for what is right. And what can you see from the data is what we should also still address. So that's what we address in the next hour, and I hope to get beyond that point because I want to also still touch on some things that we otherwise would leave out completely before the end of the course, and I don't want that. So we will go on with the image analysis and then look at something new against it. So see you in 1.5 hours. Goodbye. Thank you. No? No, it is not. I shall leave this here. Is this the next one